Hello there, and welcome to the Sleepy Space Channel. In the entire history of this species, only 12 objects have ever been seen in space before they arrived. 12. Every one of them was small, and every one gave a warning measured in hours rather than years. That number is not a statement about the sky, which has been doing this steadily since the planet formed. It is a statement about how recently we learned to look. Tonight we move slowly through the rest of it, the largest object that keeps crossing our path, the blind region toward the sun that no ground telescope is able to search, and the things still falling toward us from outside the solar system entirely. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Every one of these objects is keeping a schedule that was set long before anyone was watching. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fall away behind you. Let's begin. Part 1. The largest thing that keeps coming back. The objects that matter most are almost never the objects that are famous. This is one of the quieter truths of planetary astronomy, and it runs against every instinct a person brings to the subject. A famous object is famous because it has been watched. It has been tracked across many nights, its position recorded against background stars, its path fitted and refitted until the numbers settle. And once the numbers settle, the object is usually removed from the list of things worth worrying about. Fame, in this field, is very close to a certificate of harmlessness. The population that remains unresolved is the population nobody can name. These are the objects that are poorly measured or badly lit, or arriving from a direction that no instrument on Earth can comfortably survey. Some are small and dark, with surfaces that reflect almost no light at all. Some approach from the direction of the sun, hidden inside a glare that no ground-based telescope can look through. Some have been seen exactly once, decades ago, for a handful of nights, and then lost. Their orbits exist only as broad probability envelopes rather than as lines. The catalogue of known hazards is, in an important sense, a catalogue of solved problems. Still, the survey has to begin somewhere, and it is worth beginning with the largest of them. Not the largest object in the solar system, and not the largest comet ever recorded. The largest known object that repeatedly crosses the orbital path of Earth. That distinction belongs to a comet called Swift-Tuttle, and its dimensions are worth stating plainly because they are the reason it appears in every serious discussion of long-term planetary risk. The nucleus of Swift-Tuttle measures roughly 26 kilometers across, which is about 16 miles. That figure is worth holding still for a moment. The object generally associated with the end of the age of the dinosaurs is usually estimated at around 10 kilometers in diameter. Swift-Tuttle is roughly 2.5 times that width. Volume scales with the cube of that ratio, which means the comet is not slightly larger than the object that closed one of the great chapters of life on this planet. It is larger by a wide margin, and it is not a one-time visitor. It comes back. The returning is the sobering part. A great many large objects exist in the outer solar system, and most of them keep to distant, indifferent orbits that never bring them anywhere near the inner planets. Swift-Tuttle does not. Its orbit is a long ellipse that carries it out beyond the orbit of Pluto and then back through the inner solar system, crossing the plane and the path of Earth on each passage. It has been doing this for a very long time, and it will continue for a very long time. The word that describes such an orbit is periodic, and the period here averages about 133 years. That average, however, conceals something interesting. The period is not a clean, fixed number. It swings between roughly 128 and 136 years, wandering from return to return. The reason is Jupiter. Swift-Tuttle sits in a resonance with the largest planet in the solar system, completing one orbit for every 11 that Jupiter completes. A resonance of this kind is a kind of gravitational bookkeeping, an arrangement in which the two bodies meet in the same relative configuration again and again, and the repeated small tugs either stabilize the arrangement or slowly destroy it. In this case, the resonance appears to be protective. It shepherds the comet, nudging it back toward a path that keeps it clear of a genuinely close encounter. What is stranger is how recently this arrangement seems to have formed. The comet appears to have entered the resonance only about 1,000 years ago. Before that, it was on a less protected path. 1,000 years is nothing at all in the lifetime of a solar system, and the implication is unsettling in a quiet way. The safety of the current arrangement is not an ancient guarantee. It is a recent development in an ongoing process, and it will not last forever. The next close approach falls a little over a century from now. On that pass, the comet will come within roughly 23 million kilometers of Earth, which is about 60 times the distance to the Moon. That is comfortably distant by any reasonable measure. It will also, in all likelihood, be a fine sight. A nucleus of that size, activated by sunlight and streaming gas and dust, should be visible to the unaided eye from dark skies. People will stand outside and look up at it, and the thing they will be looking at is the largest object that regularly crosses the path of their planet. But the approach distance is not the number that matters. The number that matters is the orbital intersection distance, which measures how close the two orbital paths come to each other in space, independent of where the two bodies happen to sit along those paths at any given moment. For Swift-Tuttle and Earth, that distance is roughly 135,000 kilometers. That is closer than the Moon. The two orbits do not merely cross in the loose sense that most crossing orbits do. They very nearly touch. What separates the comet from the planet is not distance. It is timing. Timing, of course, is a fragile thing to depend on, and for a period of years the fragility looked real. When the comet last returned, a fresh recalculation of its motion suggested that a modest shift in its timing, a slip of about 2 weeks, could bring a future return into alignment with the position of Earth. 2 weeks, across a return interval of more than a century, is not a large error. Cometary orbits are genuinely difficult to predict, because comets are not inert. They vent gas as they warm, and that venting acts as a weak, uneven thruster that can push the object off a purely gravitational path. For a short period, the comet was treated as a genuine long-term hazard, and the calculation was taken seriously by people who take such calculations for a living. The resolution, when it came, did not come from a better telescope. It came from history. Observations of the same comet, recorded by skywatchers roughly 2,000 years ago, were identified in surviving records and matched against the modern orbit. Those old accounts described a bright object moving through particular constellations on particular nights, and when the positions were reconstructed, they fitted. The comet had been seen before, twice over, in an era with no instruments at all. The effect of that identification was decisive. An orbit is determined by fitting a curve to a set of measured positions, and the longer the span of time covered by those measurements, the more tightly the curve is constrained. Extending the measured arc from a few centuries to 2 full millennia collapsed the uncertainty. The 2-week slip that had made the future look open was ruled out. The threat dissolved, not because anything about the comet changed, but because more was known about where it had already been. This deserves to be stated gently and clearly, because it is one of the most quietly remarkable things in the whole subject. What resolved the calculation was someone reading records kept by people who had no idea what they were looking at. They did not know that the moving light was a body of ice and dust, 26 kilometers across. They did not know it would return. They certainly did not know that anyone, 2,000 years later, would need the note they were making. They wrote it down anyway, because something unusual had appeared in the sky, and it seemed worth recording. The deep past, kept carefully enough, becomes a measuring instrument. Even so, the comet retains its reputation. A widely repeated description calls Swift-Tuttle one of the most dangerous objects known to humanity, and the phrase traces back to a calculated worst-case energy figure. If an object of that size struck Earth at the speed a long-period comet carries, the energy released would be on the order of 25 to 30 times the energy of the impact associated with the end of the dinosaurs. The figure is not invented. It follows directly from the mass and the velocity, and comets on long orbits arrive very fast indeed. Honesty requires the rest of the sentence, though. No impact is possible for at least the next 2,000 years. The orbit is now known well enough across that span to rule it out entirely. Beyond that horizon, where prediction gives way to statistics, the per-orbit probability is on the order of 1 in 50 million. The danger is real in the sense that the arithmetic is real, and it is theoretical in every sense that matters to anyone alive. It is a number about geometry, not a number about the near future. There is a better reason to begin with this object, and it has nothing to do with hazard. Swift-Tuttle is the source of one of the most reliable meteor showers of the year, the one that arrives every August and fills the late summer sky with fast, bright streaks. That shower exists because the comet has been shedding material along its orbit for thousands of years, leaving a long, diffuse stream of dust threaded around the sun. Once a year, Earth passes through that stream, and so every one of those streaks is a grain of dust shed by a 16-mile mountain of ice that will come back. The grains are small, most of them no larger than a seed, and they burn away entirely at heights far above any weather. The shower is not something separate from the comet, and it is not a memorial to it. The shower is the comet, finely divided, arriving on schedule, lighting up for a fraction of a second, and then becoming part of the air. Part 2. The rubble pile that should come apart. There is an asteroid, currently under observation, that presents a genuine problem in physics. It is not the largest object on any watch list, and it is not the closest, and it does not have a memorable name. What it has is a set of measured properties that, taken together, should not be able to coexist. It is worth examining closely because the resolution says something about how the small bodies of the solar system are actually built. The object measures roughly 1 1/3 kilometers across, a little under a mile. Radar shape modeling, which builds a three-dimensional form by timing how a radio pulse returns from different parts of a rotating surface, gives it a slightly flattened and distinctly irregular figure, about 1.5 kilometers along its longest axis. It is not a sphere. It bulges near its equator, and it is lumpy at every scale the measurements can reach. In this respect, it resembles a great many objects of its size. The unusual property is its rotation. It turns once every 2 hours and 7 minutes. For an object more than a kilometer across, that is extremely fast. A point on its equator is being carried around the full circumference of the body in barely more than 2 hours, and the resulting outward acceleration is not negligible. To understand why this is a problem, it helps to abandon a common assumption about what asteroids are made of. Most kilometer-scale asteroids are not solid rock. They are rubble piles, loose aggregations of fragments, ranging from boulders down to fine grains, held together primarily by their own very weak gravity, with substantial void space distributed throughout the interior. Such an object might be 20 or 30 or 40% empty. It is less like a boulder and more like a slowly drifting heap of gravel that has never been compacted by anything. Spacecraft that have visited such bodies at close range have found exactly this: surfaces covered in loose stones with almost nothing holding them in place. A rubble pile of this construction has a spin limit, and the limit follows from simple mechanics. Gravity pulls material inward toward the center of the pile. Rotation carries material outward. As the spin rate increases, the outward effect grows, and at some rate, the two balance exactly at the equator, where the rotational effect is strongest. Spin any faster than that, and material at the equator experiences a net outward acceleration. There is nothing to hold it. A loose pile rotating past that limit should begin shedding material from its equator and, over time, come apart. For rubble piles of ordinary density, that limit falls at a rotation period of a little over 2 hours. This is not a theoretical convenience. It shows up in the observed data as a hard edge. Plot the rotation rates of thousands of asteroids against their sizes, and there is a clear boundary. Above roughly 150 meters in diameter, almost nothing spins faster than about 2¼ hours. The population respects the limit. It is one of the cleanest patterns in the whole catalogue. This object rotates faster than the limit. At its equator, its own gravity is insufficient to retain loose material. By the simple calculation, a body of its size and density and spin rate should not exist in its current form. It should have shed its outer layers long ago and settled into something slower and smaller, or dispersed entirely into a scattered family of fragments. And yet it is there, intact, turning steadily, and it has evidently been doing so for a very long time. The resolution is cohesion. Beyond gravity, there is a second force available to hold a pile of loose material together, the weak molecular attraction between grains in contact with one another. This is the same effect that lets fine, dry powder hold the shape of a scoop, and the same effect that makes fine dust cling stubbornly to a surface rather than falling off it. On Earth, it is almost invisible, because terrestrial gravity overwhelms it entirely. On a body a mile wide, where the surface gravity is perhaps 100,000th of what it is here, cohesion between fine grains becomes a structural force. The amount required has been estimated. Detailed modeling of how the object's surface heats and cools through its rotation, which constrains the size distribution of the grains and the thermal properties of the material, implies a required cohesive strength of roughly 60 pascals. It is important to be precise about what that number is. It is a small, positive strength, the minimum internal cohesion needed to hold the pile together against its own rotation. 60 pascals is a very small number by any engineering standard, comparable to the cohesion measured between grains of fine lunar soil. It would not support a structure of any kind on Earth. In the near absence of gravity, it is sufficient. The image worth holding is this. A mile-wide mountain of loose rock and dust is turning fast enough that the material at its equator should be lifting away, and the only thing preventing that is a force much like static cling operating between grains too fine to see. That is not a temporary arrangement or a moment caught in transition. The object has been in this configuration for a long span of time, quietly holding itself together with almost nothing. The consequences of that construction reach further than they first appear. A body held together by cohesion rather than gravity behaves quite differently when disturbed. It absorbs energy rather than transmitting it, because the void space between fragments swallows a shock instead of carrying it through. Push on such an object, and much of the effort goes into rearranging the interior. This is one of the reasons the internal structure of small bodies is studied at all. How an object is assembled determines how it responds, and how it responds determines what can and cannot be done about it. The question is not academic curiosity about a pile of gravel. It is the difference between two entirely different sets of physical behavior. The rotation itself also has an explanation, and it is a slow one. Sunlight falling on an irregular body is absorbed on the day side and re-radiated as heat, and because the surface is uneven, that re-radiation is not perfectly symmetric. The resulting imbalance produces a very faint torque, far too small to measure over any single orbit. Given millions of years, however, it accumulates, and it can spin a small asteroid steadily faster until the body approaches or crosses its own structural limit. Objects are not born rotating this quickly. They are brought there, patiently, by light. Beyond its construction, the object carries a second distinction, and it is the reason it appears on watch lists at all. It holds the highest cumulative hazard rating of any object currently tracked for long-term monitoring. That rating is not a measure of probability alone. It is a combined figure that accounts for both the likelihood of an impact and the consequence if one occurred, summed across every possible encounter in the calculated future. On that combined scale, nothing known ranks higher. The specific possibility that drives the rating is roughly 1 in 2,600 for a date about 850 years from now. Those are long odds and a distant date, and the honest framing is that the overwhelmingly likely outcome is a clean pass. But the way that number arrived at its current value is more instructive than the number itself. The probability went up. Earlier estimates placed it far lower. What changed was not the asteroid, which continued along its orbit indifferent to any of this. What changed was the reference frame. A far more precise survey of star positions became available, mapping the background sky with an accuracy that earlier catalogues could not approach. Because the position of an asteroid on any given night is measured against those background stars, improving the star catalogue improves every measurement ever made against it. Old photographic plates and old observations could be re-reduced against the better frame, and the object's past positions were recovered with much greater accuracy. The orbit tightened considerably, and the tightened orbit made the possible encounter more likely, not less. This is worth dwelling on, because it cuts against a comfortable assumption. Better knowledge does not always mean better news. An uncertain orbit is a wide band of possible futures, most of which miss. Precision narrows that band. Usually the narrowing excludes the encounter, the probability falls to zero, and the object is quietly removed from the list. That is what happens in the large majority of cases. But narrowing is not the same as reassurance. Occasionally the band narrows toward the outcome one was hoping to exclude, and the number rises. The instrument that gives certainty does not promise which certainty it will give. There is one further detail in this object's future, and it is the one that best illustrates how such calculations actually work. Roughly 700 years before the possible encounter with Earth, the asteroid passes a large main-belt object at a distance of about 450,000 kilometers. That is a little more than the distance from Earth to the Moon, which in the scale of the asteroid belt is a near miss but hardly a dramatic one. No collision, no visible effect, nothing that would look like an event. That single distant pass is nonetheless enough to matter. The gravitational tug it delivers is small, but it alters the asteroid's velocity by a tiny amount, and a tiny alteration compounded across 7 centuries of travel becomes a meaningful shift in arrival position. The uncertainty in that one encounter propagates forward into the uncertainty of the encounter with Earth. To calculate the risk properly, one must include a body that never comes anywhere near Earth at all, whose only relevance is that it will pass close to something else, hundreds of years before the moment in question. The point generalizes. The solar system is a system, not a collection of independent objects on independent tracks. Every body in it responds to every other, weakly and continuously, and the small responses accumulate over long spans into differences that matter. Nothing in it moves alone, and nothing in it can be understood in isolation. Part 3. What is already arriving? Most of what arrives from space arrives without any event at all. The large objects command attention because their arithmetic is dramatic, but they are enormously rare, and the ordinary condition of this planet is not one of waiting. It is one of steady, continuous receipt. Material from the solar system is falling onto Earth at this moment, and it has never stopped. The figure usually given is roughly 100 tons of material entering the atmosphere every day. Almost all of it is dust. The individual particles are grains smaller than a grain of sand, and many are far smaller than that, closer in size to the particles that make up smoke. They come from comets that have shed them along their orbits, from collisions between asteroids that ground larger bodies into fragments, and from the slow attrition of everything in the inner solar system rubbing gently against everything else across billions of years. Most of this material never becomes a visible meteor. A grain that's small carries very little energy, and it decelerates high in the atmosphere without ever heating enough to glow. It arrives at the top of the air, moving at cosmic speed, is brought almost to a halt within a few hundred kilometers of altitude, and then simply begins to fall. From there it drifts down slowly, taking weeks and often months to descend through the layers of the atmosphere, subject to winds and to the ordinary settling of anything very light. The origins of these grains are varied, and they can often be distinguished once the material is recovered. Some particles are fluffy and porous, loosely assembled from smaller units, and these are generally taken to be cometary, shed from ices that vaporized and released whatever was embedded in them. Others are denser and more thoroughly compacted, consistent with fragments ground off asteroids in collisions within the main belt. A very small proportion carries the chemical signature of the Moon, or of Mars, launched by impacts and eventually delivered here. The dust is not a single substance. It is a mixture drawn from the whole inventory of the solar system. Eventually, it lands. It settles on rooftops and on ocean surfaces, in rain gutters and on snowfields, on city pavements and on forest floors. Researchers who collect it deliberately look in places where terrestrial dust is scarce, in polar ice and in deep ocean sediments, because in ordinary settings it is thoroughly mixed with everything else. It is present in the dust that accumulates in any room, in vanishingly small proportion but genuinely present. Anyone reading these words has breathed it, repeatedly, without any possibility of noticing. This same dust is visible, under the right conditions, as a phenomenon called the zodiacal light. On a genuinely dark night, well away from any town, and in the hour before dawn or the hour after dusk, a faint cone of glow can sometimes be seen standing up from the horizon, tilted along the ecliptic, the plane in which the planets travel. It is not bright. It is easily mistaken for the last of twilight, and most people who have seen it have not known what they were looking at. What produces it is sunlight scattering off dust, the same dust, spread in a flattened lens through the whole inner solar system. To see the zodiacal light is to see the medium the planets move through, rendered visible only because there is so much of it strung out along such a long line of sight. And so a person standing outside before sunrise, watching a faint triangle of light lean up from the horizon, is looking at a haze of debris filling the space between the planets, some fraction of which is at that moment settling quietly onto the roof behind them. Occasionally something larger than dust arrives and stays for a while. Earth, on rare occasions, captures a small object into a temporary orbit around itself. Such objects are called minimoons, and only 4 have ever been confirmed. None is in orbit at present, though the statistical estimates suggest that at any given time there is probably at least one very small body in temporary residence, too faint to have been found. Capture is a delicate business, and the conditions are narrow. The object must approach slowly, with a velocity relative to Earth of only a few tens of meters per second, which means it must already be traveling on an orbit very close to Earth's own. It must pass near one of the gravitational balance points, where the pull of Earth and the pull of the Sun are in near equilibrium, and where an object can linger without being firmly claimed by either. Approach too fast, and it simply flies past, bent slightly and gone. Approach too slowly, from the wrong direction, and it falls in and burns. Only the narrow middle case results in a temporary orbit. The most recently confirmed of these stayed about 57 days. It never completed a full orbit of Earth. Its path was a wide horseshoe shape, curving in from one side, sweeping around the planet at a great distance without closing the loop, and drifting off again on the far side. It measured roughly 5 meters across, about the size of a small vehicle. Analysis of the light reflecting from its surface suggested something unexpected. The material appeared to match lunar rock, implying the object was a fragment of the moon, thrown off by an ancient impact and briefly returned to the neighborhood it came from. It is still traveling on an orbit much like Earth's, and it comes back for another pass in about 30 years. Distinct from these and frequently confused with them is a second category of companion. A quasi-moon is not gravitationally bound to Earth at all. It orbits the Sun, exactly as Earth does, but with an orbital period so close to Earth's that from our particular vantage point, it appears to loop around us year after year. The appearance is a matter of perspective. Viewed from a distance, the object is simply traveling its own circuit around the Sun, keeping approximate pace with a planet it is not attached to. The apparent looping is worth picturing carefully, because it is easy to misread. If the companion's orbit is slightly more elongated than Earth's, it will run a little ahead of the planet during one portion of the year and fall a little behind during another, while also rising above and dipping below the plane. Combine those two motions, and the object traces a slow, closed figure as seen from Earth, drifting outward, curving across, and returning. It never approaches. It never departs. It simply performs the same wide circuit year after year, at a distance of millions of kilometers, and the loop exists only in the frame that moves with the planet. 7 such objects are currently known. They vary considerably in size and in stability. The smallest and least stable of them is roughly 20 meters across, has occupied its present arrangement for about 60 years, and will remain in it for about 60 more before drifting into some different relationship. These arrangements are temporary in the way that most things in celestial mechanics are temporary, which is to say that they last for human lifetimes and then quietly end. One of these companions, a body a few tens of meters across, has been the subject of a long and genuinely open question about where it came from. One line of evidence, drawn from the way its surface reflects sunlight across different wavelengths, suggested that it too might be a piece of the moon. More recent modeling, together with additional spectral work, has pushed back toward an ordinary origin in the main asteroid belt. The question is not settled, and it is worth holding as an open one rather than a resolved one. A spacecraft has now arrived at the object and is surveying it from close range, with the intention of collecting and returning a sample. In due course, the argument will be settled by material in hand rather than by light, which is the most satisfying way for such an argument to end. The picture that emerges from all of this is gentler than the one the catalogues suggest. Earth is not traveling alone along its orbit. It moves in the company of a small, loose, shifting population of objects, some passing through on their way elsewhere, some briefly captured and then released, 1 or 2 keeping approximate pace for decades at a time before the arrangement dissolves. The membership changes. The company does not. The solar system is more crowded and considerably more companionable than the tidy diagrams of concentric rings imply. There is one last member of this company worth mentioning, and it is the steadiest of them. At least one small asteroid occupies the gravitationally stable point 60 degrees ahead of Earth along its orbital path. Objects in such positions are called Trojans, and the arrangement is one of the genuinely stable configurations in celestial mechanics, a place where the combined pull of the Sun and a planet can hold a small body more or less indefinitely. The stability of that position comes from a balance that is easier to describe than to picture. An object sitting 60 degrees ahead of a planet at the same distance from the Sun sits at the third corner of an equilateral triangle. Drift slightly away from that corner and the combined gravitational pull, together with the motion of the whole rotating arrangement, tends to return it. The result is not a rigid anchor, but a broad, gentle basin, and objects within it wander in long, loose paths around the balance point without escaping. Jupiter holds many thousands of such companions. Earth, being far smaller, holds very few, and finding them has taken a long time. This object is not approaching and it is not receding. It keeps station at a fixed angle ahead, traveling the same circuit at the same rate, and it has evidently been doing so for a very long time. It is also extraordinarily difficult to observe, because that position lies toward the Sun as seen from Earth, low in the twilight, buried in glare. It can be looked for only in brief windows, close to the horizon, through a great thickness of atmosphere. It is out there now, 60 degrees ahead, quietly keeping pace. Part 4. The direction we cannot look. Every survey telescope on the surface of this planet shares a single limitation, and it is not a limitation of engineering. It is a limitation of geometry. A telescope on the ground can only work when the sky above it is dark, and the sky above it is only dark when the Sun is on the other side of the world. This means that the entire practice of searching for asteroids from the ground is conducted while facing away from the Sun. The searchable sky is the anti-solar sky. The region containing the Sun and the enormous volume of space immediately around it is effectively closed to observation from the surface. The consequence of this is straightforward, and it has been understood by the people who do this work for a long time. An object approaching Earth from the sunward direction arrives inside the glare. It is lit from behind, showing us its unilluminated face, and it is embedded in a portion of sky that is filled with scattered sunlight from horizon to horizon during the hours it would be crossing. There is no practical technique that allows a night sky survey to find such an object. The telescope is not too small. The detector is not too slow. The object is simply on the wrong side of the observer. There is one narrow window, and it is a difficult one. For a short period after the Sun has set, and again for a short period before it rises, a band of sky low above the horizon becomes marginally observable. This is twilight. The sky there is not fully dark. The background is bright and changing minute by minute, and any telescope pointed into that band is looking through the thickest slab of atmosphere available, because light arriving at a shallow angle travels through far more air than light arriving from overhead. Astrometry under those conditions is demanding. The exposures must be short, the seeing is poor, and the usable time each evening is measured in tens of minutes rather than hours. As we have drifted through before, in an earlier night spent looking at what hides behind the Sun, the difficulty is not a matter of will. It is a matter of where the observer is standing. Within that closed region lives a population of objects that the night sky has almost never shown us. There is a class of asteroids whose orbits lie entirely inside the orbit of Earth. They never travel outward to the part of the sky where a conventional survey can comfortably reach them. Their entire existence is spent in the region between us and the Sun, or nearer still, circling in the bright inner portion of the solar system where our instruments have the least access. A survey designed around dark skies will find such objects only by accident and only under unusual circumstances. Only a few dozen of these interior objects are currently known. That number is not an estimate of how many exist. It is an inventory of how many have been caught, which is a very different quantity. The true population is expected to be substantially larger, and the reason is not mysterious. discovery statistics in this field follow a fairly predictable shape. When a class of object is easy to find, the discovery rate climbs quickly and then flattens because most of the population has been collected. When a class is hard to find, the discovery rate stays low and stays flat, and the flatness tells you nothing about abundance. The interior population sits firmly in the second case. Its catalogue is short because the search is hard, not because the shelves are empty. One of these objects orbits entirely inside the orbit of Venus. It is the innermost asteroid found so far, a small body threading its way around the Sun in a region where nothing else has yet been catalogued. It was found in twilight, in exactly those difficult minutes at the edge of the night, by a program built specifically to work in that band. Its orbital period is short. It completes a circuit around the Sun in a fraction of the time Earth takes, and it does so entirely within a region that ground-based astronomy had, until recently, treated as effectively unobservable. The orbital behavior of such interior bodies also makes them awkward in a second way. An object confined inside Earth's orbit spends its entire circuit at a small elongation from the Sun as seen from here, meaning the angle between it and the Sun on our sky is always modest. It can never reach opposition, the configuration in which an object sits directly away from the Sun and is both fully lit and comfortably placed for observation. The best presentation an interior asteroid can offer is a crescent, low in twilight, at a phase angle that reflects only a fraction of the light a fuller face would return. The geometry conspires twice. It puts the object in a bad part of the sky, and it shows us the wrong side of it while it is there. That discovery is representative rather than exceptional. The interior objects were essentially invisible until dedicated twilight survey programs began deliberately hunting in the awkward margins. The instruments involved were not new. What was new was the decision to accept poor conditions in exchange for access to a region nobody else was covering, and to build the observing cadence, the image processing, and the follow-up procedures around that acceptance. The population did not appear. It was simply reached, for the first time, by a method willing to work in bad light. Two arrivals demonstrated the practical shape of this gap, and both are worth setting out plainly. The largest airburst over a populated area in modern times was produced by an object roughly 20 meters across. That is a small body by the standards of this survey, a fraction of the size of the objects usually discussed in the context of hazard. It arrived from the direction of the Sun. Nothing detected it in advance, and nothing could have, because it approached along precisely the line of sight that ground-based observation cannot cover. The first warning of its existence was the light it made on the way in. The object did not reach the ground intact. It detonated high in the atmosphere, converting its motion into heat and pressure over a span of seconds. The shockwave that followed arrived at the surface some minutes after the flash, and it broke windows across a city. The great majority of injuries were caused by flying glass, and the reason is a small and very human detail. People had seen the flash, gone to their windows to look at it, and were standing at the glass when the pressure wave reached them. Almost nobody was harmed by the object itself. They were harmed by the ordinary sequence of noticing something bright and moving toward it. Separately, and on a different occasion, a considerably larger object passed close to Earth without incident. It was roughly 100 meters across, and it passed within about 70,000 kilometers of the planet, which places it well inside the orbit of the Moon. It was detected roughly a day beforehand. That single day of notice was not the product of carelessness. The object had been approaching through the sunward blind region, and it became visible only when its geometry finally carried it into a portion of sky a ground telescope could reach. Both of these events are best handled calmly, because the useful lesson in them is not dramatic. The point is not that this planet was nearly struck. In the second case, it was not nearly struck at all, A pass at 70,000 kilometers is a clean miss by any reasonable accounting. The point is narrower and more durable. The geometry of ground-based observation contains a structural hole. That hole has a known shape and a known location, and objects that arrive through it arrive without notice, regardless of how good the telescopes on the ground become. This is not a failure of diligence. It is a property of standing on a rotating planet and needing darkness to see. The remedy, accordingly, is not a larger telescope on the ground. No increase in aperture solves a problem caused by the position of the observer. The remedy is to move the observer. An infrared survey telescope placed away from Earth, operating in a location from which it can look toward the inner solar system without the sun ruining the view, can cover exactly the region that the night sky structurally cannot show us. It sees the interior population not by being more powerful, but by being somewhere else. Infrared is the correct choice for this work, and the reason follows directly from what these objects are made of. They are dark. Many have albedos of a few percent, meaning they reflect only a small fraction of the sunlight that falls on them, which is precisely why they are difficult targets in visible light. But that same darkness is an advantage at longer wavelengths. Light that is not reflected is absorbed, and absorbed sunlight warms the surface, and a warm surface re-radiates that energy as heat. In the infrared, these objects are comparatively bright. The property that hides them in one part of the spectrum reveals them in another. A dark asteroid is a poor mirror and a good radiator, and an infrared survey is built to notice radiators. A dedicated survey telescope of exactly this design is built. It is being prepared for launch within the next couple of years, and its purpose is stated without ambiguity: to find the objects that ground-based observation cannot reach, and to bring the interior population into the catalogue in numbers rather than in ones and twos. It is not a general observatory adapted to the task. It is a single-purpose instrument, designed around the survey it will perform. It is worth ending here on something plainly reassuring, stated without decoration. For almost the entirety of human history, there was no watch at all. Objects crossed near this planet and passed, and nobody knew. The systematic search for near-Earth objects is a very recent activity, younger than a great many people now living. It is already substantially better than it was 10 years ago, in the number of objects catalogued, the precision of the orbits, and the speed with which a new detection can be confirmed and refined. And the instrument that closes the largest remaining gap in that watch is finished, tested, and waiting for its ride. The blind spot is real. It is also, for the first time, being addressed by something built for the purpose. Part 5. The 12 we saw coming. The full list of objects ever detected in space before they entered Earth's atmosphere contains 12 entries. 12, across the entire history of astronomy, out of the many millions of tons of material that arrive at this planet each year. Every meteor anyone has ever watched, every fireball reported, every meteorite recovered from a field or a rooftop or a patch of ice, all of it, with these 12 exceptions, was unknown until it was already burning. The list is the complete record of a capability that did not exist at all a generation ago. Every one of the 12 was small. They were meters across, not hundreds of meters, and objects of that size are harmless in any practical sense. They cannot reach the ground intact. The atmosphere is an extremely effective shield against bodies of a few meters. The object decelerates violently in the dense lower air, heats, fragments, and either scatters as small pieces or dissipates entirely. Nothing on this list posed any danger to anyone. That fact matters, because it clarifies what the list is actually for. The significance of these 12 is not the objects themselves. It is the demonstration that the prediction chain functions end to end. Something is detected as a faint moving point among the stars. Its position is measured repeatedly across a short arc. An orbit is fitted to those measurements, and that orbit is propagated forward until it intersects the atmosphere. From the intersection, an entry time and a location on the surface are derived. Detection, orbit determination, impact point calculation, and a named place on the ground. The whole sequence, completed within hours, using an object that was an unlabeled smudge on a plate that morning. That is the achievement. The objects are merely the test articles. It is worth setting out what that sequence actually demands, because the description makes it sound tidier than it is. The initial detection is a set of positions, a few points, measured against catalogued stars, spread across perhaps an hour of tracking. From that short arc, an orbit must be fitted, and a short arc constrains an orbit poorly. There are many possible paths consistent with a handful of closely spaced measurements, and they diverge rapidly once propagated forward. Additional observations narrow the family of solutions, which is why the first task after any candidate detection is to alert other telescopes and gather more astrometry as quickly as possible. The precision required at the end of the chain is brought entirely by the number of measurements collected at the beginning. The atmosphere complicates the final step in a way that is easy to overlook. An entry point is not an impact point. The object crosses the upper atmosphere at a shallow angle, traveling many kilometers for every kilometer of altitude lost, and it continues along that path for a considerable horizontal distance while it decelerates and fragments. Any fragments that survive then fall much more slowly through the lower air, where they are carried sideways by wind. The result is that predicting where material will land requires an atmospheric model on top of the orbital one, and the recovery zone is not a point, but an elongated ellipse, sorted by mass, with the heavier pieces further along the track. The warning times involved were short in every case, and the first one set the pattern. It was found roughly 19 hours before arrival, which remains one of the longer lead times on the list. The orbit was computed, the entry corridor was identified, and the object arrived over a desert on schedule. Fragments were later recovered from the sand. That recovery was the first time material had ever been collected from an object that had been observed in space beforehand, a body whose orbit was known, whose approach had been watched, and whose pieces could then be picked up and weighed. The chain closed completely, from a point of light to a stone in a hand. The material recovered in that case proved unusual in its own right. It was a mixed assemblage, containing several distinct types of meteoritic material within a single fall, which told researchers something about how loosely the parent body had been assembled. More importantly, it came with a provenance no other meteorite possessed. Ordinary meteorites are found without history. They are stones on the ground, and their origin must be inferred from their chemistry. This one had an orbit attached, measured before arrival, which meant its composition could be tied directly to a specific path through the solar system. That linkage between a rock in a laboratory and a trajectory in space is precisely what the whole detection chain exists to make possible. Most of the others gave less. The typical warning on this list is measured in hours rather than days, and several gave only 3 or 4. That compression is not a shortcoming in the calculation. It is a consequence of size and brightness. A body of a few meters is only detectable when it is already very close, because it is faint until the final approach. The same object that becomes visible 4 hours out would have been far below any survey's limiting magnitude a week earlier. The short warning is built into the physics of small, dim things, not into any deficiency of the people watching. Those few hours also have to be spent well, and this is where the network behind the list matters more than any single telescope. A candidate flagged by a survey is not immediately known to be on an impacting trajectory. It is one of many fast-moving objects reported each night, most of which pass at a comfortable distance. Confirming that a particular one will enter the atmosphere requires follow-up observations from other sites, at other longitudes, gathered while the object is still detectable. The people involved are distributed across the world, and the work happens in the middle of somebody's night. That the process functions at all, repeatedly, under those constraints, is the substance of the achievement. One case on the list is quieter than the others, and it is worth dwelling on. An object was detected and predicted to enter the atmosphere above a sea with about 3 hours of notice. The prediction was made. A time was named, and a place was named, and the calculation was distributed to those who track such things. And then nothing was confirmed. There were no fireball reports, because there was nobody in that stretch of water to report one. No infrasound station registered the entry. No camera recorded it. No fragment was ever recovered, and none ever will be. The object arrived at the time and place specified, and was witnessed by no one. Consider the shape of that. A prediction was made about the future behavior of a specific piece of rock, in a specific portion of sky, at a specific hour. The prediction was almost certainly correct. There is no reason to think the orbit was wrong, and the arithmetic that produced it has been validated many times over on cases that were confirmed. But the confirmation never came. The moment passed over open water with nobody there to see it. Somewhere above an empty sea, a calculation came true, and the universe declined to say so. All that survives of the event is the arithmetic that anticipated it. Most of the other entries on the list were confirmed by some trace, and the variety of those traces is instructive. Several were caught by cameras belonging to amateur networks that photograph the sky continuously for exactly this reason. Others were registered by infrasound stations, which listen for very low-frequency pressure waves traveling through the atmosphere and can locate an airburst from thousands of kilometers away by comparing arrival times at separated sensors. A few produced recoverable fragments. Each of these is an independent confirmation of a prediction made hours earlier from a handful of points of light, and each one strengthens confidence in the cases where no confirmation arrives. The distribution of these 12 across time is uneven in a way that is itself informative. 4 of them occurred within a single year. The following year produced none at all. That kind of clustering, if it appeared in a longer and better populated record, might be dismissed as ordinary variance, but with a sample of 12 it is worth reading carefully, because it is not telling us anything about the sky. The sky did not change. The rate at which small objects encounter Earth is essentially constant on these timescales. Bodies of a few meters arrive with considerable regularity, and always have. What changed was the observing. Survey coverage expanded, cadence increased, and the automated pipelines that flag fast-moving objects and push them to follow-up telescopes became faster and more reliable. The clustering measures the instruments, not the population. A year with 4 detections is a year in which the watch was working well and the geometry cooperated. A year with none simply means that the few meter-scale objects that arrived did so from directions or at brightnesses that the current network could not catch in time. There is also a selection effect worth naming, because it shapes the list as much as the instruments do. Objects that approach from the night side, moving into a region of sky already under survey, are the ones most likely to be caught. Objects arriving from the sunward direction are not on this list, and cannot be, for the reasons already laid out. The 12 are therefore not a random sample of small arrivals. They are the subset whose geometry happened to place them where somebody was already looking, which means the true number of meter-scale objects reaching Earth in any given year is very much larger than the detection record suggests. Which suggests a final and honest framing for this whole segment. The capability is improving very quickly, from a starting point of essentially nothing. Within living memory, the number of objects ever seen before arrival was 0, and the idea of naming a time and a place in advance would have been treated as fanciful. It is now routine enough that the procedure has a standard shape and a standard set of participants. But the population being caught remains limited to the smallest and most harmless objects, the ones that make a bright streak and then are gone. The list is short, and every entry on it is modest, and that is exactly what an early capability looks like while it is still growing into itself. Part 6. How an orbit actually changes. The orbits of these objects are not fixed. They are worked on continuously by forces beyond the straightforward pull of the Sun and the planets, and the most consequential of those forces, for bodies of this size, is sunlight itself. The mechanism is subtle, entirely undramatic, and strong enough over long spans to determine whether a given asteroid is a concern at all. An asteroid absorbs sunlight on its daylit side. It also rotates, carrying that heated surface around toward the night side. Crucially, warming and cooling are not instantaneous. Rock has thermal inertia. It takes time to absorb heat and time to shed it, so the hottest part of the surface is not the point directly beneath the Sun, but a region rotated somewhat past it. On this planet, the same lag is why the warmest part of the day arrives in the middle of the afternoon, rather than at noon. An asteroid has an afternoon in exactly the same sense, and it is from that afternoon side that most of the absorbed energy is finally released. Radiated heat carries momentum. Every photon leaving the surface takes a small quantity of momentum with it, and the object recoils by an equal and opposite amount. If the emission were perfectly uniform in all directions, those recoils would cancel and nothing would happen. But the emission is not uniform. It is stronger from the warmer afternoon side than from the cold morning side, and that asymmetry leaves a residue. The object experiences a very small net thrust, produced by nothing more than the uneven way it gives back the light it received. The force is minute. Measured against the gravitational attraction of the Sun, it is negligible, and for any short observation it can be ignored entirely. But it is relentless. It does not vary with the seasons, it does not switch off, and it has been acting on that object continuously for as long as the object has existed, which for most of these bodies means for the greater part of the age of the solar system. A tiny acceleration applied without interruption for hundreds of millions of years is not a small effect. Over centuries, this thrust can displace a kilometer-scale asteroid by thousands of kilometers from where a purely gravitational calculation would place it. Over the timescales that matter for impact prediction, decades to a century or two, it is frequently the dominant source of uncertainty in the forecast. Gravity is known with extraordinary precision. The thermal recoil is not, because computing it requires knowing the object's shape, its surface texture, its thermal conductivity, its mass, and its spin. Those quantities are poorly constrained for almost every asteroid in the catalogue, and each one feeds directly into the answer. The direction of the drift depends on which way the object turns. A prograde rotator, spinning in the same sense as its orbital motion, has its afternoon side oriented such that the recoil pushes it gradually outward, expanding the orbit. A retrograde rotator experiences the opposite and slowly spirals inward. The two cases produce drifts of similar magnitude in opposite directions, which means that a small error about the spin axis produces a large error about the future. To predict where an asteroid will be in 100 years, it is not enough to know where it is and how fast it is moving. You must also know which way it turns. It is worth sitting with the plainest statement of this. Sunlight steers asteroids. The same illumination that makes them visible, that allows them to be catalogued at all, is also acting on them continuously, nudging them along, adjusting their paths across geological time. The thing that lights them is also, very slowly, aiming them. The strength of the effect also scales with size, which sets the range over which it matters. The thrust acts on the surface, while the resistance to being moved depends on the mass, so the acceleration produced falls off as the object grows. For a body a few meters across, the drift is substantial and can reorganize an orbit within a comparatively short span. For a body several kilometers across, it is nearly irrelevant, swamped by the sheer inertia involved. The objects for which this force is decisive are the middle range, tens to hundreds of meters, which is precisely the size range that dominates hazard assessment. The mechanism is most influential exactly where the stakes are highest, which is an inconvenient arrangement but a real one. That accumulated drift matters most where the geometry is delicate, which brings us to the concept of a keyhole. A keyhole is a small region of space that an object must pass through during one encounter with Earth in order for a later encounter to become an impact. It is not a place where anything happens. It is a place where a particular deflection happens, where Earth's gravity, acting on the passing object, bends its path by exactly the amount required to bring it back into resonance with Earth's position at some specific future date. The precision involved is what makes keyholes strange. Threading one requires arriving at a very particular point with a very particular velocity. Pass slightly inside it and the orbit is bent a little too much. Pass slightly outside and it is bent a little too little, and in either case the object returns later to find the planet somewhere else entirely. Keyholes can therefore be extremely small. A keyhole, a few kilometers wide, can sit inside an approach corridor thousands of kilometers across, which means that the overwhelming majority of possible trajectories through that corridor lead nowhere at all. This explains why risk assessments for these objects behave in ways that seem counterintuitive. When a probability is quoted for a distant encounter, it is very often not the probability of hitting Earth. It is the probability of passing through a small region during an earlier, entirely safe approach, the chance of threading a needle that would set up a collision much later. The number is a statement about a geometric window, not about a collision, and it changes rapidly as the orbit is refined, because refining the orbit shrinks the region of uncertainty around the corridor and either includes the keyhole or excludes it. Bennu is the clearest working example. It is roughly 500 meters across, a rubble pile rather than a solid body, held together loosely by its own weak gravity and studied more thoroughly than almost any other object of its kind. A spacecraft visited it, mapped it in detail, and returned a sample of its surface material to Earth. It is, by a considerable margin, the best characterized hazardous asteroid in the catalogue. Bennu makes a very close approach in about 110 years, passing at roughly 200,000 kilometers. That places it comfortably inside the distance of the Moon, close enough to be an extraordinary observing opportunity and far enough that there is no possibility of impact at that pass. The approach itself is not the concern. What matters is that during the pass, Bennu must miss a keyhole roughly 5 kilometers wide. Threading that narrow window would bend its orbit into a resonance that could produce a possible impact roughly 50 years afterward. The probability of that outcome is about 1 in 2,700, a number that describes the chance of hitting a 5-kilometer target during a pass 200,000 kilometers out, and which exists as a number at all only because the thermal drift discussed a moment ago cannot yet be pinned down more tightly. The returned sample turned out to be scientifically remarkable in ways unrelated to any of this. It contained a substantial inventory of organic material, most of the amino acids that life on Earth uses to build proteins, and all of the nucleobases that carry information in genetic material. It also contained a set of salts, including minerals never previously seen in an extraterrestrial sample. Those salts are the significant detail because they could not have been recovered any other way. They would have been destroyed had the material arrived here as a meteorite, altered by the heat of entry, and then dissolved by contact with terrestrial water and air. They survived only because the material was collected in space, sealed, and carried down inside a container. The canonical keyhole story, however, belongs to Apophis, and it belongs here as an illustration of the mechanism, rather than as a headline. Apophis is roughly 340 meters across. For a brief period, it was rated the most concerning object ever tracked, occupying a higher position on the standard hazard scales than anything before or since, on the strength of an orbit that was then known only from a short observational arc. It makes an exceptionally close approach in a few years' time. It will pass inside the orbits of geostationary satellites, nearer to the ground than the ring of communications spacecraft that hold station above the equator. An object of that size at that distance is a genuinely unusual event. It will be visible to the unaided eye from parts of Earth, appearing as a moving point that shifts perceptibly against the background stars over the course of an evening. No one now alive has watched a naked-eye asteroid cross the sky. The keyhole that would have set up a later impact has been ruled out. Refined tracking removed it, by narrowing the orbital solution until the small region in question fell outside the range of possible paths. The mechanism did not change, the measurement improved, and the improved measurement showed that the needle was never going to be threaded. The pass is now purely an opportunity, and several spacecraft are being directed to observe it, to watch, at close range, how a rubble pile responds to being pulled on by a planet. That is the arc worth carrying away from this part. An object went from the highest-rated hazard on record to a scheduled observing campaign, and nothing about the object altered in the interval. No orbit was adjusted, no deflection attempted, no intervention made. What changed was the quality of the measurements, and the quality of the measurements changed the future, because the future was never uncertain in itself. It was only uncertain to us. Part 7. The ones that are not quite asteroids. The categories astronomers use are conveniences, and the sky does not honor them. An asteroid is a rock. A comet is an icy body that grows a coma and a tail when the sun warms it. That division held for a long time, and it served well enough while the instruments were coarse and the sample was small. It has been coming apart, quietly, for several decades now. The more carefully these objects are observed, the more of them refuse to sit on either side of the line. Some rocks behave like comets. Some comets look exactly like rocks. And a few of them do things that neither definition anticipated at all. Consider Phaethon. It is a body roughly 5 to 6 kilometers across, which places it among the larger objects that cross Earth's orbital neighborhood. It is classified as an asteroid, and by every conventional measure of composition and reflectance, it deserves that classification. Its surface appears rocky. Its density appears consistent with stone rather than ice. Nothing about its bulk properties suggests a comet. And yet its orbit is unlike any other named asteroids, and that orbit is the reason it behaves the way it does. Phaethon travels closer to the Sun than any other named asteroid. At its closest approach, it comes to roughly a seventh of Earth's distance from the Sun, which places it well inside the orbit of Mercury. Mercury itself, the innermost planet, never comes that close. Phaethon crosses that space on every circuit, plunges through it, and climbs back out. The orbit is steeply eccentric, a long ellipse that reaches from the asteroid belt down into the hottest region of the inner solar system and back out again. Nothing else in its class does this. At that distance from the Sun, the physics of the situation becomes uncompromising. The surface temperature of Phaethon at perihelion reaches roughly 750 degrees Celsius. That is hot enough to glow. The rock does not merely warm, it radiates in the visible, a dull red heat across the sunward face, the color of iron in a forge. Minerals at that temperature begin to break down. Volatile compounds locked in the surface layers are driven off. Thermal stress cracks the outer material, because the day side and the night side differ by hundreds of degrees, and the rock expands and contracts against itself with every rotation. That thermal stress is probably the key to the whole object. Rock is a poor conductor of heat, which means the outer few centimeters of Phaethon's surface heat and cool far faster than the material beneath them. The surface layer therefore expands, while the layer below it does not, and the resulting strain works at the material along whatever flaws already exist in it. Over many circuits, this fractures the surface into progressively smaller pieces. The process has a name, thermal fatigue, and it is the same mechanism that breaks paving stones over years of freezing and thawing, operating here at far greater intensity and across a far longer span of time. Phaethon has been doing this for a very long while. And near perihelion, Phaethon brightens. It brightens more than a simple warming rock should, and it develops a tail. For a body classified as an asteroid, that behavior is anomalous enough to demand explanation, and the obvious explanation is that Phaethon is a dormant comet with some residual ice buried beneath its crust. That explanation seemed reasonable for a long time. It turns out to be wrong, or at least incomplete. When the tail is imaged through filters designed to pick out dust, the dust is not there. There is no meaningful quantity of scattered particles in the tail at all. What the filters do detect is sodium. The tail is made of sodium atoms, baked out of the surface by the heat and fluorescing in sunlight, glowing at their own characteristic wavelength, the way a street lamp glows. It is a tail of metal vapor. No ice, no dust, no sublimating volatiles in the usual sense. Simply an atom of sodium leaving a rock too hot to hold onto it, and then shining. Sodium is well suited to this role. It is a comparatively volatile element for a metal, driven out of silicate minerals at temperatures that would leave iron and magnesium entirely untroubled. Once free, a sodium atom absorbs sunlight at a very specific wavelength and re-emits it almost immediately, which makes even a thin population of such atoms conspicuous to an instrument tuned to that wavelength. The same emission is what gives older street lighting its distinctive orange color. So Phaethon's tail is bright in one narrow band and effectively invisible everywhere else, which is precisely why it took particular observations to establish what the tail was made of, rather than merely that a tail existed. There is a further consequence, and it is the one most people encounter without ever knowing its origin. Phaethon is the parent body of the December meteor shower, which is among the most reliable displays of the year. Meteor showers are supposed to come from comets. A comet sheds ice and dust along its orbit. Earth crosses that debris, and the particles burn up in the upper atmosphere. That is the standard account, and for nearly every shower it is correct. The December stream is the exception. Its source is an asteroid, not a comet, and how a rock supplies a meteor stream of that density is a question not entirely settled. Picture the situation from the ground. It is a cold, clear night in the middle of winter, in the northern hemisphere, when the air is dry and the sky is as transparent as it ever gets. The meteors arrive at a steady rate, dozens each hour, entering the atmosphere and burning out in a second or less. They are dependable in a way that few celestial events are. They arrive on schedule, in quantity, year after year. And the source of that dependability is a rock, several kilometers wide, that at this moment in its orbit may be glowing dull red on its sunward side and shedding a faint tail of sodium vapor into space. The connection between the two things is real, and it is not obvious, and it took a long while to establish. And beyond Phaethon, the taxonomy dissolves further. There is a class of objects, only recognized in recent years, that has come to be called the dark comets. Roughly 14 are currently known, which makes this one of the smallest recognized populations in the solar system. They were identified not by what they look like, but by how they move. The identifying signature is non-gravitational acceleration. If an object's position is tracked carefully enough over enough orbits, its path can be compared against the trajectory that gravity alone predicts. For nearly all asteroids, the two match. For a comet, they do not, because a comet outgasses. Material sublimating from the sunlit side leaves in one direction, and by conservation of momentum, the nucleus is pushed in the other. The comet is, in effect, a very weak and very inefficient rocket, thrusting continuously for as long as it is warm enough to sublimate. Over many orbits, that thrust accumulates into a measurable deviation. The dark comets show that deviation. They drift off the gravitational path in exactly the manner outgassing would produce. But when they are imaged, there is nothing to see. No coma, no tail. No visible envelope of gas or dust surrounding the nucleus. They present as perfectly ordinary asteroids, points of reflected sunlight with no extended structure whatsoever. Something is leaving these objects in sufficient quantity to steer them, and it is not producing any of the visible signatures that outgassing normally produces. Measuring such an acceleration is delicate work. The deviations involved are minute. A body may end up a few hundred kilometers from its predicted position after an entire orbit, against a path many hundreds of millions of kilometers long. Detecting that requires positions measured to high precision across many years, and it requires that every other source of error be understood and removed. The gravitational influence of the larger asteroids must be accounted for. The exact reference frame of the star catalogue must be consistent. Only when all of that has been done does a residual remain, and only then can it be attributed to something the object itself is doing. Within that small population, there appear to be two distinct groups. One consists of larger bodies on stretched, elongated, comet-like orbits, reaching well out into the outer solar system and back. The other consists of small objects, all of them under about 50 meters across, traveling on far more circular paths that keep them near the inner planets. The two groups differ in size, in orbit, and probably in origin. Whether they share any common mechanism beyond the acceleration itself is unclear. One line of thinking is that the smaller group are fragments of the larger. A body on a stretched orbit that breaks apart would leave pieces that are gradually circularized over long spans by repeated planetary encounters, and the resulting small objects would retain whatever residual ice their parent carried. The size limit is suggestive here. All the small ones are under about 50 meters, which is roughly the scale at which a rotating body can be spun apart by sunlight pressure alone. Fragments produced that way would be numerous, small, and difficult to detect, which matches what is observed. This remains a proposal rather than a conclusion. And then there is the reclassification that reframed the whole category. One of these objects had been tracked for a very long time, nearly 3 decades of accumulated observations, a well-determined orbit, a settled place in the catalogues. When astronomers went to look for it during a later apparition, it was not where those decades of observation said it should be. The discrepancy was small, but it was real, and the object had been quietly diverging from its predicted position. Follow-up observation was arranged using substantially larger telescopes than had been used before. And with that additional aperture, the picture changed. There was a coma, thin, faint, but unmistakably present. There was a tail, long and extremely diffuse, extending away from the nucleus in the anti-solar direction. Both had been there all along. Neither had ever been detected, because no instrument of sufficient sensitivity had ever been pointed at the object during the right part of its orbit. It was reclassified as a comet. The implication deserves stating plainly. Some fraction of the dark comet population may not represent a new class of object at all. They may be ordinary comets, weak ones, faint ones, ones with low activity levels and thin atmospheres, that nobody had yet examined with a large enough instrument. The acceleration was always the signature of outgassing. The absence of a coma may simply have been the absence of sufficient telescope. This is worth sitting with, because it is how a great deal of astronomy actually proceeds. A category of mystery objects partly dissolved the moment someone looked harder at one of its members. Not every strangeness in the sky is a new kind of thing. Some of it is an old kind of thing, insufficiently observed, waiting patiently for an instrument equal to it. The dark comets remain a real and interesting population, and some of them may yet prove genuinely novel. But the lesson of that one reclassification is a modest and useful one. The universe is under no obligation to be as strange as our first look suggests. Sometimes it is stranger. Sometimes it is only fainter. Part 8. The Swarm and the Airburst. There is a large comet nucleus that returns to the inner solar system every century or so, and each time it passes, it leaves a trail of fine debris strung out behind it, and that trail is what produces the August meteors that people watch from summer fields. Elsewhere, a rubble pile a mile across turns on its axis faster than its own gravity should permit, held together by forces that are not quite gravity and not quite anything simple. Every day, roughly 100 tons of dust settles onto the Earth without anyone noticing, most of it too fine to see, arriving continuously and having always arrived. Toward the Sun, there is a region of sky that no ground-based survey can search, because the daylight there is overwhelming, and objects approaching from that direction remain invisible until they are past it. Only 12 small objects have ever been detected before they arrived, out of an enormous number that have arrived. And sunlight itself, absorbed on one side of a spinning body and re-radiated on the other, exerts a pressure so faint it takes millennia to matter. But it matters, steering orbits by small increments toward or away from the narrow keyholes in space that determine whether a distant encounter becomes a close one. That last point about debris strung along an orbit is worth developing because it explains something visible from any dark field. A comet on a repeated orbit does not shed its material and leave it behind in one place. The particles it releases inherit almost exactly the comet's own velocity, with small differences, and so they spread gradually along the entire orbital path until the whole ellipse is populated with a thin ribbon of dust. Earth crosses several of these ribbons at the same points in its own orbit each year, and each crossing produces an annual meteor shower, arriving on the same dates because the geometry repeats. The debris in these streams is not evenly distributed. It clumps. Material released during one particularly active perihelion passage stays roughly together, forming a filament denser than the surrounding stream, and that filament drifts slowly under the influence of the planets. In some years, Earth passes through a dense concentration and the shower is strong, producing hundreds of meteors an hour. In other years, it passes through a thin region and the same shower is unremarkable. The difference is not in the Earth and not in the comet, but in which part of the ribbon the crossing happens to intersect. The finer structure of these streams can be modeled with reasonable success. Particles released at a given perihelion passage can be traced forward, accounting for the gravitational influence of the planets and for the pressure of sunlight, which acts more strongly on smaller grains than larger ones, and therefore sorts the debris by size over time. The smallest particles are pushed outward and eventually driven from the solar system altogether. The larger ones persist. This means an old stream is systematically coarser than a young one, and the meteors it produces are correspondingly brighter and slower to burn out. The character of a shower is a record of the age of the material producing it. And among these streams, one is distinctly unusual. There is a meteor complex that is far wider and far older than the others, a diffuse stream associated with a short-period comet, spread across a broad region of space rather than confined to a narrow ribbon. Its width is the clue to its age. Streams disperse over time, and a stream this dispersed has been evolving for a very long while. The prevailing understanding is that the complex represents the remains of a much larger parent body that fragmented, with the surviving comet being only one piece of an originally far more substantial object. Within this broad old stream there appears to be structure. A denser concentration of material seems to be held in a resonance with Jupiter, which means the concentration and the planet complete their orbits in a simple numerical ratio, and Jupiter's gravity acts to keep the material gathered rather than dispersing it. Earth's path takes it closer to this concentration in some years than in others, on a cycle of a few years, and observations of the associated meteor activity broadly follow that cycle. The open question, and it is genuinely open, is whether that concentration contains larger objects alongside the dust. The parent body was substantial. Fragmentation does not produce only fine particles, it produces a spectrum of sizes, and the larger pieces would be dark, small, and difficult to detect at the distances involved. Whether such objects exist within the concentration, how many there might be, and how large, are matters of ongoing observational work rather than settled fact. It is an unresolved question in the ordinary scientific sense, a thing not yet measured, being measured. Progress on it will come from patient survey work rather than from any single decisive observation. The concentration occupies a broad region of space, and searching it means covering a large area of sky repeatedly at times when the geometry is favorable, looking for objects that are dark, small, and moving against a crowded background of stars. Each candidate found must then be tracked long enough to establish whether its orbit genuinely belongs to the complex or merely resembles it. This is slow, unglamorous work, and it accumulates a little at a time. That is how most questions of this kind are eventually settled, not resolved at a stroke, but gradually narrowed as the surveys deepen and the catalogue fills in. And that leads to the question of what happens when an object of modest size does encounter the Earth, because the answer is not what most people assume. A little over a century ago, an object entered the atmosphere above a remote and largely uninhabited stretch of forest. It exploded before reaching the ground. The blast flattened roughly 2,000 square kilometers of trees, laying them down in a radial pattern pointing outward from a central point, trunks aligned like iron filings around a magnet. The event was recorded on barographs and seismographs across 2 continents. The region was remote enough that the first scientific expedition did not reach the site for many years afterward, and what it found was not what anyone had expected. At the center of the flattened area, the trees were still standing. They had been stripped of branches and bark, reduced to bare vertical poles, but they had not been knocked down. That detail is diagnostic. It means the shock front arrived from directly overhead at that point, pressing downward along the axis of each trunk rather than against its side. Farther out, where the same front arrived at an angle, the trees went over, and the angle of their fall traces the geometry of the blast outward in every direction. The pattern maps the event as precisely as any instrument could have. There is no crater. This has occasionally been treated as a puzzle, and it is not one. There is no crater because the object never reached the ground. As it descended through progressively denser air at enormous speed, the pressure on its leading face rose steeply, and at some altitude, that pressure exceeded the mechanical strength of the material the object was made of. It came apart. Fragmentation increased the surface area presented to the air, which increased the drag, which increased the pressure further, which drove further fragmentation. The process runs away in a fraction of a second, and the object's entire kinetic energy is deposited into the atmosphere as heat and shock rather than into the ground as an impact. That is an airburst. This is the general case rather than the exception. Stony objects below roughly a few tens of meters across almost never reach the surface intact. They disintegrate at altitude, and what arrives on the ground is a scatter of small fragments moving at ordinary falling speeds, if anything arrives at all. The atmosphere accomplishes this despite being, by mass, a very thin layer indeed, a column of air weighing about as much as 10 meters of water. The reason it works is speed. Air is compressible and yielding at the velocities of everyday experience. Against an object moving at 20 kilometers per second, it is not yielding at all. At that speed, the air has no time to flow out of the way. It piles up ahead of the object, compresses, heats to many thousands of degrees, and pushes back with a force that stone cannot survive. The atmosphere is not a thin film against such an object. It behaves like a wall. And so the atmosphere is, functionally, a shield, and it has been operating continuously for the entire history of life on this planet. It required no design and no maintenance. It does not need to be aimed or activated or funded. It absorbs the small arrivals, which is nearly all arrivals, without anyone being aware that it has done so. The 100 tons of dust each day is the shield working at the lowest end of the size range. The occasional fireball seen crossing the night sky is the same process at a slightly larger scale. Several such fireballs occur every day somewhere above the Earth, most of them over ocean or over ground where nobody happens to be looking upward at that moment. Networks of automated cameras now record a steady catalogue of them, and the great majority end exactly the same way, in a bright terminal flash at high altitude and nothing further. The atmosphere handles them without difficulty, as it has handled every one of their predecessors. There is a structural comfort in this that is worth stating clearly. The thing that has protected the surface of the Earth through every era of its living history is not vigilance and not technology. It is the air. It was working before anyone thought to look upward and name what they saw, and it has continued working through every night that anyone has ever slept beneath it, without interruption and without instruction. Part 9. The Long Fall from the Outer Dark. The solar system does not end at the outermost planet, and it does not end at the belt of icy bodies beyond it. It ends, if it ends anywhere, at the outer edge of a roughly spherical shell of frozen material called the Oort cloud, which surrounds the Sun in every direction and extends outward to a substantial fraction of the distance to the nearest stars. It is not a disk. The planets orbit in a plane, and the objects of the Oort cloud do not. They occupy a shell, arriving from any direction at any inclination. The objects out there are bound to the Sun, but only barely. At those distances, the Sun's gravitational grip has weakened to almost nothing, and the orbital velocities are correspondingly small. A body may take millions of years to complete a single circuit. As we have drifted through on an earlier night, out past the boundaries of the solar system, the influence of the Sun becomes comparable to the influence of passing stars and the broader gravitational field of the galaxy itself. A small perturbation is enough to alter one of these orbits substantially. A nearby star, drifting past at a distance of a light year or two, over a period of tens of thousands of years, can nudge a body just enough to turn its slow, wide circle into a long ellipse that falls all the way in. The scale of the reservoir is difficult to convey with ordinary comparisons. Estimates place the number of bodies out there in the trillions, though the figure is inferred rather than counted, derived from the rate at which long-period comets appear in the inner system and worked backwards. Not one of these objects has ever been directly observed in place. They are too small, too dark, and too distant for any existing instrument. The entire population is known only through its emissaries, the individual bodies that fall inward, become briefly visible, and then either return to the outer dark or do not return at all. And this is where the genuinely difficult problem in this entire subject lies. Asteroids are, on the whole, a tractable case. They are found, catalogued, and then tracked across decades. Their orbits become known to high precision. Once an object's path is established, its position can be projected forward for a very long time, and the warning available for any close approach runs from years to centuries. The work is enormous, and the surveys are incomplete, but the method is sound, and the timescales are generous. A long-period comet falling in for the first time is a different situation entirely. It is not in any catalogue. It cannot be, because it has never been in the inner solar system during the era of telescopes, and possibly never during the era of anything that could have recorded it. Its orbit has not been measured because there has been nothing to measure. Until it announces itself, it does not exist as far as any survey is concerned. It becomes detectable only when it is close enough to the Sun for its ices to begin sublimating. Out in the deep cold, it is a dark nucleus of ice and dust, a few kilometers across, reflecting almost no light and radiating almost none. It only becomes visible when solar heating begins to turn its surface ices directly to gas, producing a coma, an expanding envelope of gas and entrained dust that is enormously larger than the nucleus and enormously brighter. That transition typically begins somewhere around the orbit of Jupiter or Saturn. From that point, the fall inward is measured in months rather than years. The comet is moving fast because it has been accelerating toward the Sun for a very long time, and the final approach through the region of the giant planets is comparatively brief. The realistic warning time for a previously unknown long-period comet is on the order of 1 to 2 years, and it can be considerably shorter than that depending on the geometry of the approach and the sky position at the time of detection. They also arrive faster than asteroids do, often at twice the speed or more, because they are falling from far greater distance and have converted far more gravitational potential into velocity. Kinetic energy scales with the square of speed. An object arriving at twice the velocity carries 4 times the energy for the same mass. A comet nucleus of quite ordinary size, therefore, represents a great deal more energy than an asteroid of matching dimensions. The geometry compounds this. Asteroids travel in roughly the same plane as the planets and in the same direction around the Sun, which means an encounter is usually a matter of one body overtaking another, and the relative speed is only the difference between 2 similar velocities. Long-period comets have no such courtesy. They arrive from any direction on the sphere, including head-on, and a head-on approach adds the 2 orbital speeds together rather than subtracting them. The distribution of possible encounter velocities is therefore much wider and reaches much higher at its upper end. And the deflection strategies that have been developed for asteroids do not transfer to this case. Every one of them, the kinetic impactor, the gravity tractor, the slow application of a small force over a long baseline, requires decades of lead time. They work by making a tiny change to a trajectory very early, so that the tiny change has room to grow into a large one. With 1 or 2 years of notice, there is no room. The methods are not merely difficult in this scenario, they are geometrically inapplicable. This is the most genuinely unresolved item in this survey, and it would be dishonest to resolve it artificially. There is no current capability that addresses it. There are proposals, and there is research, and there is a great deal of thoughtful work on rapid response architectures, but there is no system standing ready. That is the honest state of the matter, and it should be left standing as such. What can be said, calmly and truthfully, is this. That has been the state of affairs for 4.5 billion years. The Oort cloud has been dropping bodies inward for the entire history of the solar system, at whatever rate it drops them, long before anything here was capable of noticing. The ground beneath the listener has been here through all of it. The arrangement is not new, and the odds it represents are the same odds under which every generation has lived and slept. And within that reservoir, some of the objects are very large indeed. The largest Oort cloud nucleus yet found is somewhere between roughly 120 and 140 kilometers across. An ordinary comet nucleus is a few kilometers. This body is a small world by comparison, and it is by a wide margin the largest object of its kind ever identified. It reaches its closest approach to the Sun in about 5 years, and that closest approach is just outside the orbit of Saturn. It does not enter the inner solar system, and it never will on this passage. It will turn around at a distance greater than the ringed planets and begin the long climb back out toward the cold from which it came. It will never be visible to the unaided eye. Despite its size, it will remain faint, because it stays far away and because it reflects little light. At its brightest, it requires a substantial telescope to observe at all, never brighter than Pluto, which is itself well beyond naked eye visibility. The largest comet nucleus known will pass through its perihelion without a single person seeing it without instruments. It is also active, and that is the more interesting fact. It was found to be outgassing carbon monoxide at more than 16 times Earth's distance from the Sun. At that distance, water ice is not a volatile at all. It behaves like rock, hard and inert, and would remain so indefinitely. Carbon monoxide sublimates at far lower temperatures, and it is that far more volatile ice driving the activity. The object undergoes repeated outbursts, shedding enormous quantities of material in periods shorter than a day, brightening and then fading as the released material disperses. And there is a population that connects the outer reservoirs to the comets of the inner system. Between the orbits of Jupiter and Neptune sits a group of icy bodies on unstable paths, called the centaurs. They cross the orbits of the giant planets, and consequently the giant planets shuffle them. Each close passage alters the orbit, and no orbit lasts. Their dynamical lifetimes are only a few million years, which is a very short interval by solar system standards. None of them originated where they are now, and none of them will remain. They are the transitional population. Objects move inward from the outer reservoirs, spend a few million years being knocked about among the giant planets, and emerge either ejected from the solar system entirely or captured onto shorter orbits as the short-period comets. Every short-period comet was very likely a centaur once. The region between Jupiter and Neptune is where the transformation happens. One of the centaurs is known for near-continuous outbursts. It brightens dramatically and without evident pattern, over and over, on timescales of weeks, and it has been doing this for as long as it has been watched. The energy source is not fully settled. Crystallization of amorphous ice is the leading candidate, a phase change that releases heat and can propagate through the interior, but the details remain unresolved. Amorphous ice forms only where material freezes at extremely low temperatures, trapping gas within a disordered structure. Warmed even slightly, it rearranges into ordinary crystalline ice and releases both that trapped gas and a quantity of heat which can warm the neighboring material enough to convert it in turn. It sits out there beyond the orbit of Saturn, brightening and dimming and brightening again, a body in slow transition between one part of the solar system and another, working through a process that has not yet been entirely explained. Part 10. The visitors from outside. Everything we have followed so far belongs to the Sun. The asteroids, the comets, the fragments and the dust all move on paths the Sun has drawn for them, and every one of those paths eventually closes. That is the defining quality of a bound orbit. An object may take a year to complete its circuit, or 100,000 years, but it comes back. It falls inward, it whips around the Sun, it climbs out again, and gravity slows it just enough that it never quite escapes. The Sun holds everything on a very long leash, and the leash always pulls. But not everything moving through this part of space belongs here. Some objects arrive from outside the solar system entirely, cross through it once, and leave. They do not return. They were never bound to the Sun to begin with, and the brief encounter changes their direction without capturing them. They are travelers passing through a territory that has no claim on them. The measurement that separates these two categories is orbital eccentricity. Eccentricity describes the shape of a path. A perfect circle has an eccentricity of 0. An ellipse, stretched but still closed, has an eccentricity somewhere between 0 and 1. Nearly every object in the solar system falls in that range. Earth's orbit is almost circular. A long-period comet may swing out on an ellipse so elongated it takes tens of thousands of years to close, but close it does. At an eccentricity of exactly 1, the path opens. It becomes a parabola, and the object is moving at precisely the speed required to escape the sun forever, arriving with no energy to spare. Above 1, the path is hyperbolic. The object is moving faster than escape velocity, and it will leave the solar system with speed remaining. It came in with excess energy, which means it came from somewhere else. That is the whole test. Measure the orbit carefully, calculate the eccentricity, and the number tells you whether the object was born here or arrived from another star. Solar system comets occasionally reach eccentricities a hair above 1, nudged there by the gravity of Jupiter or Saturn on their way out, but the excess is tiny and the origin is still local. A genuine interstellar object announces itself with an eccentricity that is not marginally above 1, but decisively above it. Only 3 such objects have ever been confirmed. 3. In the whole history of astronomical observation. The first was found on its way out. By the time anyone recognized what it had already rounded the sun and was accelerating away, and the observing window that remained was measured in days rather than months. Telescopes worldwide turned toward it and gathered what they could before it faded past the limit of detection. What they gathered was strange. The object was small, at most a few hundred meters in its longest dimension, and it tumbled as it went. The brightness rose and fell dramatically as it rotated, and the depth of that variation implies a shape. A round object shows almost no variation. An elongated object shows a great deal, because the reflecting area changes enormously between the broad view and the end-on view. The variation measured here was extreme. The most straightforward reading is a body several times longer than it is wide. Nothing in the solar system has that proportion at that size. Asteroids are irregular, certainly, and some are distinctly elongated, but the ratio implied here sits well outside the familiar range. There is no confirmed explanation. Formation processes have been proposed, and tidal disruption by a passing star has been proposed, and none of them has settled the question. The object is gone, and it took the answer with it. It also showed no coma and no tail. A comet approaching the sun heats up, its volatile ices turn directly to gas, and that gas carries dust with it into a visible envelope. This object produced nothing detectable. It looked like a bare rock. And yet, as it departed, its motion did not match a purely gravitational trajectory. It accelerated slightly, gently, in the direction away from the sun, by an amount too small to see over a short arc and too consistent to dismiss over a long one. That kind of acceleration is the signature of outgassing. Something was venting from the surface, producing a faint thrust. But no coma appeared, which means whatever was venting carried no dust and produced no easily detectable emission. Various volatiles have been suggested that would behave this way, escaping quietly without the usual visible display. The idea is plausible, unproven, and now untestable, since the object will not come back. The second interstellar visitor was almost the opposite in character. It was found on its way in, which allowed months of observation rather than days, and everything about it was familiar. It had a coma. It had a tail. Its composition, measured across a broad set of molecules, sat comfortably within the range of ordinary solar system comets. It behaved exactly as a comet from our own outer regions would behave, warming as it approached, brightening steadily, then fading as it withdrew. The remarkable thing about it was how unremarkable it was. That sounds like a small finding, and it is not. The first visitor had suggested that objects from other stars might be fundamentally alien in construction, that other systems might build things we could not recognize. The second visitor argued otherwise. Here was a comet formed around a different star, in a different disk of gas and dust, under a different set of conditions, and it looked like ours. The ices were the ices we know. The dust behaved the way our dust behaves. That is genuine information about the universe. It suggests that the process of building comets is common, and that the chemistry available in a young planetary system is broadly similar from one star to the next. 2 data points is not a survey, but a single normal example still tells you that normal is possible. And then there is the third, which is the most thoroughly studied of the 3, by a wide margin. It is under 1 kilometer across, and critically, it was detected while still inbound. That gave observers a long campaign, many months of watching an object from another star as it approached, rounded the sun, and departed, with the full instrumentation of modern astronomy trained on it the entire time. What that campaign found is a comet unlike anything in the solar system. Begin with what it was venting. Comets are dominated by water ice. Water is the primary volatile, and carbon dioxide is usually a secondary component. In this object, the proportions were reversed to an extreme degree. Carbon dioxide dominated the outgassing, and the ratio of carbon dioxide to water measured here ranks among the highest ever recorded for any comet from any origin. That is not a small deviation from the familiar pattern. That is a different pattern. The metal content was unusual as well. Nickel vapor was detected in the coma with no accompanying iron. In ordinary circumstances, those 2 metals travel together because they appear together in the minerals that make up rocky bodies, and separating them requires specific conditions. Nickel without iron is chemically odd. It points to a formation environment or a set of surface compounds that does not match what our own comets carry. And the water itself is heavy. Hydrogen comes in more than one form. The common form has a single proton in its nucleus. The heavier form, deuterium, has a proton and a neutron, and water built with deuterium in place of ordinary hydrogen is measurably heavier. The proportion of deuterium in a body's water is one of the most reliable fingerprints available, because that proportion is set at formation and does not easily change afterward. The deuterium fraction in this object's water is roughly 30 times that of typical solar system comets, and more than 40 times that of Earth's oceans. Deuterium becomes enriched at very low temperatures, through chemical reactions that favor the heavier isotope only when there is almost no thermal energy available to overcome that preference. An enrichment of this magnitude implies formation in conditions extraordinarily cold, colder than the outer regions where our own comets were assembled, in a place where the chemistry had a long time to run at temperatures close to the floor. There is more, and it concerns age. The velocity of an object relative to the general motion of stars in this part of the galaxy carries information about its history. Stars that formed recently move in relatively orderly fashion, following the flow of the galactic disk. Stars that have been circulating for billions of years accumulate gravitational nudges from every passing mass, and their motions become progressively less orderly, more inclined, more scattered. Astronomers use this to sort stellar populations by age without ever examining the stars themselves. This object's motion through the galaxy is characteristic of an old population. It is not traveling with the young, orderly flow. It is moving the way something moves after a very long time. Age estimates derived from this span a wide range, and the uncertainty is genuine, but the lower bound sits at around 7 billion years. That is older than the Sun. The upper end of the range extends considerably further, into the earlier history of the galaxy. Consider that carefully. This is material that was assembled around a star that had already formed, lived, and in all likelihood ended before our own Sun began to condense from its cloud. It has been drifting between the stars for longer than our solar system has existed, carrying its cold chemistry unchanged, and it passed through here once. And it behaved throughout like a comet. That deserves emphasis. It developed a coma as it warmed. It grew a dust tail, pushed back by the pressure of sunlight, and an ion tail, swept into alignment by the solar wind. Its outgassing produced a small non-gravitational acceleration of exactly the kind and magnitude that sublimating ice produces. It did not fragment. It did not behave erratically. Every measurement made of it is consistent with a natural body of ice and dust, formed by ordinary processes around a different star, in a colder place, a very long time ago. That is what makes it valuable. Not novelty, but comparison. We have exactly one detailed record of how a planetary system assembles, and it is our own, and a single example teaches you very little about what is typical. Every interstellar object that passes through is a sample from a system we will never visit, delivered free of charge, requiring only that someone be watching. And that brings the widening. These three objects arrived within a handful of years of one another, and it is natural to read that as a change in the traffic. It is not. There is no reason to believe the flow of interstellar material through this region has increased at all. Objects like these have presumably been crossing the solar system for its entire history, at some steady and unremarkable rate, arriving and departing with nobody to record them. What changed is on this end. Survey telescopes reached the sensitivity and the sky coverage required to catch faint, fast objects on short arcs. The software learned to flag orbits with impossible eccentricities. The alert networks learned to move quickly enough that follow-up could begin before the window closed. 3 in a handful of years, after 4.5 billion years of them going by unseen. The sky did not get busier. Someone finally opened their eyes. Part 11. What can actually be done? The question that hangs over everything in this survey is whether any of it can be answered. It is one thing to catalogue the objects crossing Earth's path, and quite another to do something about one. For most of human history, the honest answer was that nothing could be done. The answer changed recently, and it changed by experiment rather than by argument. The experiment was straightforward in concept. A spacecraft, roughly the size of a vending machine, was flown deliberately into a small moonlet orbiting a larger asteroid. The choice of target was the clever part. Measuring whether you have altered the path of a lone asteroid around the Sun is extremely difficult, because the change is minute against an orbit that takes years to complete. But a small moon circling a larger body completes its orbit in hours, and that period can be timed with real precision from Earth by watching the pair eclipse one another. Measure the period before, hit the moonlet, measure the period after. The difference is the answer. The moonlet is roughly 160 meters across. That size was not accidental either. It sits in the range that matters most for planetary defense, large enough to devastate a region on impact, small enough that objects of that size remain substantially uncatalogued. The pair posed no threat to Earth whatsoever, before the experiment or after it. That was a requirement of the design. The spacecraft navigated its final approach autonomously. At the distances involved, radio signals take too long for anyone on Earth to steer. The target was too small and too dim to be resolved until the last hour, so the vehicle had to identify the moonlet against the larger asteroid on its own and correct its own course and hold aim through the final seconds. It did. The images returned in the last moments showed a surface of loose rock and boulders growing to fill the frame, and then transmission ended. Then came the measurement. The orbital period of the moonlet around its parent had been shortened, and shortened by substantially more than the pre-impact predictions had allowed for. The experiment did not merely succeed. It overperformed, and understanding why turned out to be as valuable as the deflection itself. The extra effect came from ejecta. When the spacecraft struck, it did not simply transfer its own momentum and stop. It excavated the surface, and an enormous quantity of material was blasted outward at high speed. That material carried momentum away from the moonlet, and by conservation of momentum, the moonlet was pushed in the opposite direction. The recoil from the ejected debris contributed more push than the spacecraft itself did, more than doubling the effect of the collision. Telescopes watched the plume develop over the following days and weeks. It expanded. It was swept back by sunlight into a long tail, and the asteroid pair briefly resembled a comet. Within that plume, careful imaging identified something more specific: a swarm of boulders, dozens of individual meter-scale rocks, drifting away from the impact site slowly enough to be tracked as separate objects. Those boulders carry a meaningful share of the total momentum budget, and their distribution is not random. It reflects how the surface was assembled and how it came apart. Later analysis suggested something further. The moonlet appears to have been measurably reshaped by the impact. Not simply cratered, with a bowl excavated in an otherwise intact body, but deformed, its overall figure altered, material redistributed across its surface. That is the behavior of a rubble pile, a body held together by mutual gravity and weak surface forces rather than by any coherent internal strength. Strike a solid rock and you make a crater. Strike a loose heap and you rearrange it. Which delivers the lesson, and the lesson is a complication. Deflection efficiency depends heavily on the internal structure of the target. A solid body and a loose aggregate of the same mass respond quite differently to the same impact, and the difference is not a small correction. It is a factor that changes the answer. And internal structure is precisely the property most difficult to determine from a distance. Brightness tells you something. Rotation tells you something. Radar can hint at density. None of it tells you with confidence how a given body will behave when struck. The experiment is only half finished. A second spacecraft is now arriving at the same system to survey the aftermath in detail, to map the crater, or to establish that no simple crater exists, to measure the moonlet's mass properly, which converts the observed velocity change into a precise measure of efficiency, to probe the internal structure directly. Only with those numbers does the demonstration become a calibrated tool rather than a successful stunt. And beyond kinetic impact, there are other methods, quieter and slower, and in some ways more elegant. Consider the gravity tractor. A spacecraft is stationed near an asteroid and simply remains there, holding position. It touches nothing. It fires nothing at the surface. It uses only its own mass and the mutual gravitational attraction between spacecraft and asteroid to draw the asteroid gradually onto a new path. The force is almost absurdly small. The acceleration would be undetectable over any short interval. But it is continuous, and it is precisely controllable, and continuity applied across years accumulates. The great advantage of the gravity tractor is that it does not care what the asteroid is made of. It cannot fragment a rubble pile because it never touches it. It works identically on solid rock and loose gravel. Where a kinetic impact carries genuine uncertainty about how the target will respond, gravity does not negotiate. It pulls, and the asteroid follows, and the only variable is how long you are willing to wait. There is also ion beam shepherding. A spacecraft hovers near the surface and directs a stream of accelerated ions at the asteroid. The ions strike, transfer their momentum, and push the body continuously without any contact. It is gentler than an impact and considerably stronger than gravity alone, and like the gravity tractor, it can be run for as long as the spacecraft has power and propellant, adjusted and monitored throughout. All of these methods share a single requirement, and it is not the one most people expect. It is not energy. It is not technology. It is time. The reason is geometric. Deflecting an asteroid does not mean shoving it out of the way. It means changing its speed very slightly, so that over the remaining years it arrives at the crossing point a little early or a little late. Earth moves about 30 kilometers every second. A miss of a few minutes is a miss of thousands of kilometers. And a few minutes of timing, accumulated over decades of travel, requires a velocity change so small it barely deserves the name. Applied decades ahead, a velocity change smaller than a walking pace is sufficient. A push you could not feel, sustained or delivered once, quietly rearranges the arithmetic of a collision until the collision does not occur. Applied months ahead, nothing is sufficient. The same push produces a shift of a few hundred kilometers, and the object arrives exactly where it was always going to arrive. State it plainly, warning time is the resource. Everything else in planetary defense is downstream of that. The rockets exist. The navigation works. The physics is understood and has now been tested in flight. What cannot be manufactured on demand is the decades of notice that make the physics useful. This is why the surveyed telescopes matter more than the interceptors. Finding an object 30 years early is worth more than any conceivable spacecraft launched 3 months out. And there is a recent case that shows the whole system operating end to end. A small object, roughly 60 meters across, was detected and tracked, and as its orbit was refined, it began to show a genuine chance of hitting Earth. The probability climbed over a period of weeks, and at its peak it stood a little over 3%, the second highest impact probability ever recorded for this planet. That is not a large number in absolute terms. It is an enormous number by the standards of this field, where anything above a fraction of a percent is exceptional. Then more observations arrived, the orbit tightened further, and the probability fell away to nothing within days. This is the ordinary behavior of these calculations. Early on, the uncertainty region is a long corridor through space, and Earth occupies some fraction of it. As observations accumulate, the corridor narrows. Usually Earth falls outside the narrowed corridor, and the probability collapses to zero. Occasionally, on the way there, it rises first, because the corridor is shrinking around a region that still contains us. A rising probability is not evidence of danger closing in. It is evidence of a measurement being refined. Attention then shifted to the Moon. The corridor that no longer touched Earth still touched the Moon, and for a period, the probability of a lunar impact rose above 4%. That was not a safety concern in any conventional sense, but it was scientifically extraordinary. The prospect of watching a known object of known size strike a known surface, with instruments prepared in advance. Resolving it required an observation of remarkable difficulty. The object had moved far from Earth and faded past the reach of ordinary telescopes, and it was recovered in infrared at a brightness that constituted the faintest detection of a near-Earth object ever made. That single campaign cut the remaining positional uncertainty by a factor of more than 30, and it eliminated the lunar possibility entirely. The object will pass the Moon by roughly 20,000 kilometers. The modeling done while the possibility was still live deserves mention because it was serious work. An impact of that size on the lunar surface would have excavated a crater roughly a kilometer across. It would have thrown a substantial quantity of material off the Moon entirely, since lunar escape velocity is low, and a fraction of any large ejector plume simply leaves. That material would have temporarily raised the debris flux in near-Earth space over the following years, a modest effect, and a measurable one, and precisely the sort of consequence nobody would have thought to model without a specific occasion. That is the arc worth holding on to. A probability rose. It was taken seriously rather than dismissed. Resources were allocated, a genuinely difficult observation was made, and the possibility dissolved under better measurement. Nothing was hidden, and nothing needed to be. That is the system working exactly as it was designed to work. Part 12. The Slow Monsters. Not everything arriving at Earth is solid, and not everything arriving can be deflected. Some of what crosses this space is material of a different order entirely. Particles, fields, and structures so large that the vocabulary of impact and avoidance stops applying. The Sun releases a continuous stream of charged particles, flowing outward in every direction at hundreds of kilometers per second. This solar wind never stops. It has been blowing across Earth for the whole existence of the planet, and it shapes the environment out to the edge of the Sun's influence. Occasionally, though, the Sun does something more emphatic. A region of its atmosphere becomes magnetically unstable, the field lines reconnect and snap, and an enormous cloud of magnetized plasma is thrown outward, billions of tons of it, traveling at hundreds of kilometers per second, and sometimes considerably faster. Such a cloud crosses the distance to Earth in a day or two. When it arrives, it meets the magnetosphere, the region of space controlled by Earth's own magnetic field, and the field does what it has always done. It deflects the oncoming particles around the planet. The magnetosphere compresses on the sunward side, streams out into a long tail on the night side, and the great majority of the arriving material is turned aside. Some of it is not. Along the field lines that converge on the polar regions, charged particles funnel downward and collide with atoms in the upper atmosphere. Those atoms are briefly excited, then release the energy as light, green from oxygen at one altitude, red from oxygen higher up, blue and violet from nitrogen. The aurora is that process made visible. The curtains and arcs are not arbitrary shapes. They trace the geometry of the magnetic field itself, drawn in light by particles following invisible lines. The most powerful geomagnetic storm on record produced effects that remain instructive. Telegraph systems were the only extensive electrical networks then in existence, and the storm induced currents in their long wires strong enough to disrupt them entirely. Operators found their equipment behaving impossibly. Some disconnected their batteries and continued sending messages on the induced current alone, the sky powering the line. Elsewhere, equipment sparked, and in some offices, the sparks set paper alight. Aurorae were reported close to the equator, far outside the polar regions where they properly belong. The event is remembered because the modern world is built on conductors. Power grids, pipelines, and communications networks all consist of long conducting paths, and a changing magnetic field induces current in every one of them. A storm of that magnitude arriving now would be an infrastructure problem of considerable scale. It is one of the few arrivals in this entire survey that can be prepared for directly. Grids can be reconfigured, satellites can be placed in safe modes, and the warning time, though short, is real. And beyond the storms, there is a quieter traffic, passing through continuously. Cosmic rays are atomic nuclei accelerated to extraordinary energies, arriving from supernova remnants, from the environments of massive black holes, and from sources not yet identified. They are not rays in any ordinary sense. They are individual particles moving at very nearly the speed of light, and the most energetic among them carry energies that laboratory accelerators cannot approach. The most energetic single particle ever recorded carried roughly the kinetic energy of a thrown baseball. That energy, which would be entirely unremarkable distributed across the atoms of a ball, was concentrated into one atomic nucleus. There is no confirmed account of what accelerates a particle to that state. When a cosmic ray strikes the upper atmosphere, it collides with a nucleus in the air and produces a shower of secondary particles, which collide in turn and produce more, cascading downward through the atmosphere in a widening cone. A single primary particle can generate billions of secondaries, spread across kilometers of ground. Some of those secondaries reach the surface. Several are passing through the listener's body every second, arriving from the sky, crossing tissue, and continuing into the earth below. And then there are neutrinos, which make the cosmic rays seem heavy-handed by comparison. Neutrinos are produced in enormous quantities by fusion in the sun's core, where hydrogen nuclei combine into helium and release them as a byproduct. They carry almost no mass, no electric charge, and they interact with matter only through the weakest of the fundamental forces. They stream outward from the core, passing through the entire body of the sun as though it were not there, and cross to Earth in a little over 8 minutes. Roughly 100 trillion of them pass through each person every second. That is not a figure of speech. It is a rate, and it is continuous, and it applies equally at noon and at midnight, since the ones arriving at night have simply passed through the whole planet first without noticing it. Almost none of them interact with anything at all. In an entire human lifetime, perhaps a handful will happen to strike a nucleus in the body and register. The rest pass through the bed, the floor, the foundations, the rock beneath, the core of the earth, and out the other side into space, unchanged and unimpeded. Consider the picture that makes. The listener is lying still. The room is dark and quiet, and nothing is moving. And through that stillness, at this exact moment, a flux of particles from the center of the sun is passing continuously and silently, 100 trillion every second, arriving from a fusion reaction 93 million miles away, crossing the body without touching it, and continuing on through the planet. Nothing is happening. Nothing has ever happened. It is the most crowded stillness imaginable. And beyond the particles, there is something on a slower schedule altogether. An orange dwarf star, smaller and cooler and dimmer than the sun, currently sits a little over 60 light-years away. It is unremarkable in almost every respect except one. It is moving toward the solar system, and its path will bring it closer to us than any star has ever come. In roughly 1.33 million years it will make its approach. At closest passage it will be somewhere around 10 to 13,000 times Earth's distance from the sun, which sounds enormous, and is enormous, and is nonetheless well inside the outer Oort cloud. The star will not merely pass nearby. It will pass through the outermost territory the sun still nominally holds. That is closer than any known star has ever come, or is projected to come, across the entire past and future history of the solar system. Every other stellar encounter reconstructed from the motions of nearby stars is more distant. This one is the record in both directions of time. The consequence is expected to be gravitational. Objects in the outer Oort cloud are bound to the sun very weakly, at distances where the sun's grip is barely stronger than the general pull of the galaxy. A passing star at that range perturbs them. Some orbits are stretched, some are tilted, and some are turned inward, sending comets falling toward the inner solar system over the millions of years that follow. The magnitude of that effect is uncertain. Estimates vary considerably, depending on assumptions about the density and structure of the outer cloud, which are themselves poorly constrained. The perturbation is expected, its size is not agreed. What can be said with confidence is that the number of long-period comets entering the inner system will likely be elevated for a long stretch afterward, a slow, statistical increase spread across a period longer than our species has existed. Notice what makes this a correct answer to the question this survey began with. It is an object. It is heading toward us. Its arrival will genuinely alter conditions in the solar system, and it will do so on a timescale in which no human question survives, not the questions of any individual, not of any nation, not plausibly of the species. The star is coming, and it is coming at a pace that renders concern structurally impossible. And there is one larger still. The Andromeda Galaxy is approaching the Milky Way at roughly 110 kilometers per second. It is the largest object heading toward Earth by any definition anyone could construct. 1 trillion stars, bound together with gas and dust and dark matter, 2.5 million light-years away, falling toward us under mutual gravity. Nearly every galaxy in the observable universe is receding as space expands between us. Andromeda is not, because at this distance, the local gravitational attraction between the two galaxies overwhelms the expansion. The two have been falling toward one another for a very long time, and they will continue to. The encounter is billions of years away. And when it comes, stars will almost certainly not collide. The distances between stars are so much greater than the sizes of stars that two galaxies can pass through one another with essentially no direct contact. The galaxies will interpenetrate, their gas clouds will collide and compress and form new stars in bright bursts. Their spiral structures will be pulled into long streamers by tidal forces, and eventually, after further passes, they will merge into a single larger galaxy. From the surface of a world in either galaxy, the change would be gradual beyond any capacity to notice. Earth's sky will alter slowly, over hundreds of millions of years, as Andromeda grows from a faint smudge, barely visible on a dark night, into a structure spanning the sky. Every generation would see essentially the same sky its parents saw. Only across geological spans would the difference become apparent. As we have drifted through on an earlier night, measuring the space between the galaxies, the numbers are not built for intuition. They are built for patience. The distance closes at 110 kilometers every second, which is genuinely fast, and it is still a journey of billions of years, because the distance is what it is. Which brings this survey to its final observation. Every object described across this entire video is on a schedule. The spinning asteroid, the fragmenting comet, the interstellar visitor from an older star, the orange dwarf drifting toward the Oort cloud, the galaxy falling toward this one, each is following a path set by gravity long before anyone existed to observe it, and each will keep that path long after. The monsters are real. Every one of them is a genuine object with genuine mass, moving on a genuine trajectory, and the physics is not negotiable. And they are also patient beyond any human capacity for patience. They have been coming for millions of years, or billions, and they will continue coming at exactly the same rate whether anyone watches or not. Nothing in this survey is in a hurry. Nothing in it ever has been. That patience is the thing to fall asleep to. And so we leave them all where they are, the spinning mountain held together by almost nothing, the star falling slowly toward the edge of our cloud, the great wheel of Andromeda drifting closer while nobody hurries. Not one of them is in any rush, and neither, tonight, are you. Let your breathing slow. Let the sky keep its own schedule. Sleep well, and good night.